Let's go to Deep Learning for NLP Lecture 5. Today we see Encoder-Decoder and attention, two super cool things that are going to build up to the next lecture, which is going to be very heavy, I already told you, because we see the transformer architecture and some stuff. So what do we see today? What do we see today? Windows help me. Okay. What do we see today? We apply the RNNs to NLP tasks. Nothing new. We did it last time as well. But we want to see how we can apply RNNs to some tasks. And now for other tasks, we just cannot. So we can understand some of their limitations, right? Because at the end, when it's the last lecture, it's all cool, like, oh, the model is perfect, nothing is wrong. Then we see the encoder-decoder models, so a new architecture. This architecture is cool because it can overcome some of the limitations that we'll see in the first part. And finally, we'll see the attention mechanism. So we learn basically how to give some specific importance, how to weight the importance of specific words while processing the text. So how to pay attention to the important part of what we are reading, which kind of mimics in a very creative way what we do as humans, okay? Okay, so it was already a question. Okay, so first one, applying RNNs to various NLP tasks. So let's go back to lecture 1 when we saw NLP task. You remember they have sentiment analysis, whatever. Basically, we can we say there are so many tasks, but mostly there are two families. Does anyone remember what families those are? Yeah. Yeah, text classification and text generation. But let's take another perspective, okay? So let's consider NLP tasks not in terms of whether we generate or classify, but by how many input we do to our model, we feed into our model, and how many outputs we obtain. So does anyone wants to think what are the options? If I don't say any task, but just say how much stuff enters in the model and how much stuff exits out of the model. Can you think of like some distinctions, some cases that we can have? Hint, there are only 3 cases that are all bound to the output. Okay. It's actually pretty easy, but I think maybe you're a bit shy. So we obtain 3 cases. Classification, which is we have whatever inputs, but only one output. Labeling, which is we have whatever input and the exact same amount of outputs. And generation, which is we have 2 different amounts of input and output, where M might be longer or shorter than the input, okay? So to give you another view, you can see something like this, right? So classification, think about understanding the sentiment of a sentence, understanding NLI. Does anyone remember what NLI is? Let's see how fresh you are. Yeah?
Natural language inference. NLI.
Yes, it's written, but what's the task?
So, to predict if it's contradiction, entailment, or neutral.
Yes. If the consequence comes after the hypothesis, is entailed, contradictory, or neutral. We have hate speech detection, you know, all kind of things where you have a sentence, you have one label, yes or no, positive or negative, entailment or contradiction, or neutral, toxic or not toxic, whatever. Then we have labeling, where we have the same amount of inputs and outputs. So part of speech tagging, is this a verb, is this an adjective, is this a noun? And so, of course, for each single token, we need to output a label. Named entity recognition, we saw it in the first lecture as well. You know, like these are a person, this is an organization, this is a place. Code switching tagging, super cool. For example, Korean and Indian are, for example, lots of like languages with you either code switch, so you switch languages, you code mix, so you can start using, you know, 70% of the sentences in Indian, but like 4 words are in English. And it will be cool to, like, you know, tag every single token and say, oh, this is English, this is Indian, this is English, this is Indian. And then we have sequence generation. So you can get creative. We can translation, summarization, chatbots. And here is not meant that we're gonna have the same amount of input, because if I take well, summarization, it's obvious, right? It wouldn't be a summary if the output would be the same length of the input, or would be the most useless summary ever. The same for chatbots. You don't ask like ChatGPT, will I pass deep learning for NLP, and it tells you exactly the same amount of words. But so If we have this task, can we solve them with RNN? So let's start from classification. Who has an idea or remembers, because we actually saw it before, a way to solve a classification task with an RNN? So we have a sentence or whatever, and we need to produce one output. How do we do it with an RNN? Okay, tough crowd today. Well, we saw it last time. We use this, which is what we defined as an acceptor. So you plug into your RNN, you encode the entire sequence, and then you transform the final representation usually into a probability distribution over your classes. So just plug into your softmax or your NLP, whatever. Okay, now that I reminded you this, do you remember how do we do labeling? Okay, yeah.
Is it where we get an output for every input there and then with softmax? Like for me, it's visually easier to look at the graphics to have under classification pending instead of us having those white hats under every node. We put every output into a software, so simply that.
Yeah, something similar. Yes. So you have something like this. Every output at every cells, you calculate the loss because now you have a ground truth for every single element of the sentence, and then you do some sum of the losses, you some combination. However, how do we do it for generation? Come on, get creative. I prefer someone who says something completely wrong, but still say something. Yeah.
Train on a data set, data as the inputs, and then you generate new amount of output always generated from the train.
Okay, so you train on a certain data set, you generate a certain amount of outputs. Do you see a problem in how RNN works? How does an RNN work? Like I feed an input, then I obtain a state and an output, and then what happens? Like if I feed the first word, obtain a state, an output, what do I do then? I pass the state and I repeat. Then I repeat. Is there a problem with this? Anyone? I saw some hands before. Yes?
I think we discussed vanishing gradient, I think.
Yeah, the vanishing gradient, but to be honest, this is just recurrent network. We could use an LSTM that kind of really minimizes that. There is one problem with this, that RNNs produce as many outputs as they get as inputs. So if I want to process 5 words and produce 20, I cannot. If I want to encode 20 words and produce 5, I cannot. If I don't know, even if I don't even know how long the output sequence should be, I cannot do it. I'm bound to produce 10 inputs, 10 outputs, 100 inputs, 100 outputs, 1 input, 1 output. See the problem? Is it clear? And yes?
But solve this problem naively, I would just declare some kind of empty word.
Yeah, okay, you're up to something. We're gonna actually see that. But yeah, you can define some kind of empty words, but it's not great. Yes?
What you said is we assume can encoder-decoder approach, but if we just go for an autoregressive decoder approach,
but we didn't even see what that is yet. We're talking about RNNs, basic ones. So yeah, you're a bit ahead.
Yeah,
so.
but RNNs, it's like you generate the next word and then you feed it the next step. That's just
Sorry, come again?
when you generate the word, then you feed it the next step.
Yeah.
And then you continue doing it. You can do that with an RNN, and if you have flexible.
Wait. I think I'm missing what you're saying. How is it flexible if for a simple RNN? We're talking in the context of simple RNN or simple STM, not an encoder-decoder. So it's like,
You can feed the output, the input, and then have some end of sequence token that you usually generate.
okay. So I see these are all valid things. You can have some either in an end of sequence token. They're not ideal. So we're gonna see why, and we're gonna see how we can fix it. But first, just to clarify these RNNs, we solve the problem that we can basically have on however large or short, long or short sequence you want. But we cannot separate the length from that output, at least not natively. So we have many instances in language when this happens, as we discussed. Like, for example, you can see here a translation, like I will never put pineapple on pizza, I'm not crazy, that's 10 words. And if the translator I used is good, there's actually 12 words in German. So you already got that, some of your colleagues already got that. We can solve this with a couple of dirty fixes, okay? So if I need to produce something which is longer than the input, what I can do is using what is called a pad token. So basically, I add a certain amount of these tokens to the input, and then I can just keep processing, because it doesn't matter if my sentence stops at 10 words and there are 20 pads token. I can now produce up to 30 token, 10 plus 20. How many? You can use an heuristic, you can check your longest sequence in your data set. You can make some assumption. Maybe you don't have enough compute to produce more than 200 words. So that's a hard limit. The other case, what if I want the output to be shorter than the input? Well, I use the end of sequence token. So let's say I produce still 50 words, but the 10th is the end of sequence. I cut everything, and then I have my thing. So in theory, the problem is already solved. So why do we need to think about something else? Can anyone think about some issues? Yes?
Yeah, it's a question and an answer. Wouldn't the last point about output being shorter, like just basically waste performance, waste generation?
Yes, that's indeed one of the points. There's a lot of wasted computation. So if I assume my longest sequence is 2,000 words, even when I need to produce 3 words, I produce 2,000 and throw them in the bin, right? So it's a bit not a great approach, a bit dirty. Yes?
Stop in computation. Finish. What would happen? Progress to it.
Well, no, in theory, no. I mean, depends on how you implement it, but normally in a normal land, you need to do the whole process, right? It has a couple of steps. Yes?
Would we randomly set certain nodes to 0 somewhere within the process, or at the first step?
You want to randomly set, what do you mean by randomly set some inputs to 0?
So cut in the middle of the complete process. So if any node produces an output and it gives it to the next step, we could, before even going to the softmax or even before processing those, we could just stop randomly.
Okay, I see. So basically you say, I just do something in the code that if I see the end of sequence, I set everything to 0, destroy there, and then whatever. Somehow I block the further processing, right?
But if I have an RNN that produces 2,000 token outputs, and I know I need to send it to 10 outputs, then I could tell 1,990 of my nodes to go to 0 and stop working.
Okay, yeah, you could do that. The point is that you're talking about, so you called after the 10 words, set everything to 0 and stop it working. But the point is you're talking about inference. It's different when we talk about training your RNN. And when you train your RNN, you need to set up an input length, a max input length. So still you're going to train the RNN to produce 2,000 tokens, even for sentences which are like 2 tokens or 5 tokens. So that you cannot stop, because you cannot alter the RNN training, because what do you do then? You set the gradient to 0, but then it hurts the backpropagation. It gets messy, right? So, yeah. Yeah, sure.
How do you know where to set the EOS token if you don't know how long the output?
Okay, how do you know where to set the EOS token? You add it to all the sentences in your data set and trust that the RNN will learn during training that at some point the most probable token is in end of sequence. Like it will see a lot of things like I am fine, end of sequence. So when we produce something like I'm not so well, you will kind of understand that there's an end of sequence there. Another problem is that this does not generalize well. So you have to assume the longest sequence. So even there, you could find a longer one, have to retrain from scratch. But also you're polluting the learning of the network, because in theory, we want the network to learn meaningful linguistic pattern. But if we think pad is sometimes 2 pads after the end of sequence. Sometimes it's 1,000 pads, sometimes it's 5. it starts putting a lot of confusing information inside what pad models linguistically, when the fact is the pad should be an empty token. It shouldn't model anything. And also, yeah, we saw it's wasteful. So this is why with a traditional RNN, we can kind of go around it. We can do some dirty fixes, but it's better to do something a bit cleaner, which just solves the problem. Good news, we can with the encoder-decoder. So this is the encoder-decoder, and the idea is that now you have not one but two RNNs. One is called the encoder, and is the one that you will see here. And what the encoder does is reads the input and produces its usual states, okay? And then you have a decoder. The decoder produces the output one token at a time, which means that now we separate the parameters of the two networks. So this one and this one as different parameters. They are trained together, you will say, but they are kept separate, right? And this is also true because this is also good practice because they should learn different things. Now, ideally, the encoder is more about modeling the state, some kind of overall representation of the sequence, while the output, the decoder should learn how to produce an output from that. And now the decoder can just stop generating because the decoder is only working in function of itself. It's not receiving 3,000 words. It just gets a state and starts generating. Then when you produce the end of sequence, you can just stop. You don't have future tokens to process. So you see the point? Yes, was right? Yeah.
Basically, it sends out its inputs, the decoder, I mean.
Yes. Yes, we're gonna see it now, but yes, basically every time the decoder produces an output, you refeed back that output to the decoder and keeps. Yeah.
So the encoder would still need padding?
The encoder, no. The encoder does not need because the encoder does not need padding anymore because you just need to process the sentence in one time. So but you mean in the training during the training, yes, but that's kind of okay because I mean it's not perfect, but at least now you're producing states rather than also generating the output. So in theory, you can discern a bit better that the pad has no meaningful information because if you have a ground truth to produce and you see that if you give a lot of importance to this padding token, nothing really changes, issue automatically collapse. Whether if you use the padding to actually be functional to generation, then it gets a bit messier. There were other questions? Yes?
On the decoder, what are the inputs?
We're gonna see it in a bit. What are the inputs of the decoder? Yeah?
What is the state?
Sorry?
What is the state?
What do you mean?
Represent the input?
We're gonna see that in a bit. So we're gonna see in a bit what are the inputs of the decoder and what is the state that we model. Okay? Anything? Everyone is scared that I will answer to everything. We'll see it soon. Yeah?
You don't actually know what state should come out, right?
You never know what state. So your colleagues ask, how do you train the encoder? You don't know what kind of state is good. Yeah, but you have a ground truth. So you trust your model to learn a state. It's forced on the learning. Since the state it changed the back propagation, the parameters should always produce the best state, right? As you reduce the loss, that's the cool thing about machine learning. You don't need to know. You're just forcing. As soon as you're reasonably certain that there is a relationship to exploit, the data makes sense. Yes.
I think we trained end to end, right? So we trained the encoder based on encoder's output.
Yes, but I think your colleague was more asking like, how do you even produce a state that makes sense, right? But this is back to the RNNs, right?
Answer my question. Yes.
Okay, then we stop the other way.
I wasn't aware that. So I thought we separated them to also train them.
No. You do the whole pass. You don't separate them. So when you train, you do the whole pass encoding and decoding. Okay, so some of you already asked. We need a way to initialize the decoder. So you can see it here. Probably you can get an int. Usually you just use the last state of the encoder, and that's the first state of the decoder, rather than, I don't know, it wouldn't make sense to initialize it all to 0, because then if you just do at 0 here, what's the point of doing all of this if you just throw it in the bin, right? And what else? As I said, we can copy the last encoder state, but we can also apply a function to it, a linear transformation or a nonlinear transformation. Why? Well, as usual, to learn more complex pattern, you may decide to just pass that through another layer just to see if you can model or change that in another way. But it's also useful if your encoder and decoder has different dimensionality, like if the vectors of the encoder have 100 dimension and with the ones of the decoder have 50 dimension. Why should we do that? Personally, now it's not made a lot, but maybe in the past you had limited resources and you realized that to model Spanish, 50 dimension were enough, but for, I don't know, Chinese, you need much more. And so now you have an encoder, decoder, they operate in different dimensions. But if I get 100 dimensions here and the decoder produces 50 dimensions, I need a transformation, right? I need to project it down. So that's also a reason why you could have it. What are the inputs of the decoder? There was another question. The previous outputs of the decoder. So this is just what basically you call an autoregressive model, which you're going to see in a bit. What is the initial input of the decoder? Because, okay, here we have a state, so we have an initial state, but this doesn't produce anything, right? We don't have an output. So how do we initialize it? Beginning of sentence. That's always the case. So of course you format your dataset so every sentence becomes beginning of sentence, sentence, end of sentence. And so the decoder always starts from BOS. So Encoder-Decoder are also, as your colleague was saying before, the models that you call autoregressives, which basically they use outputs produced in the past to predict the future ones. This works extremely good to model text. In fact, we've been trying to get out of autoregressive models and try to find something better for years, but still, even GPT models today, they are autoregressive. So they do this, right? So I want you now to think a bit, what can go wrong with this, with the autoregressive? He was ready, he was waiting for this. Yes, tell me.
I mean, if a model produces a wrong token very early on, all of the subsequent tokens will be just wrong as well.
Yeah, so if you produce something bad, you start re-putting it back and polluting the whole process, right? So that's exactly the problem. This is actually something that today produces a lot of various issues. One of the most famous one is very trendy is called hallucination or confabulation. Is that part when ChatGPT gaslight you into writing some very, very elaborate nonsense. So yeah, we have something for this, which is called teacher forcing, that we can use at least during training to solve the issue. So assume that we generate some text with an encoder-decoder. For example, we're translating some stuff. So what we'll do is that we will feed it to the encoder the input. We will produce a state, then we pass it, we produce the second one. So I will never put pineapple on my pizza. It's crazy. And at some point, we process the input, completely. We will get a final state that we initialize the decoder with. Now, I feed the beginning of sentence token to the decoder, and I produce something wrong. So I don't speak German, but I use translations. Translation. This is not I. This is like we or something, or they or something like that. And now it's an error. But now I'm going to feed that error to the decoder, and maybe that error is going to propagate to produce more and more errors. And we are basically doomed. Does it completely destroy the training? No, because then the loss is going to be horrible and you're going to redo again. But it slows down learning. It's a problem. It makes us waste resources. So teacher forcing fixes this by feeding the desired, the ground truth token instead. So no matter what our decoder produced, we're going to feed the right one. Is it cheating? No, because it's during training, so it doesn't matter. We're going to use it for the loss. It's just to adjust the state and the production of the outputs. So it stabilizes training, it blocks the error propagation, and empirically also speeds up the learning. With most time, no meaningful problem. I think there are some papers in machine translation that show you that it may hide some warning patterns, but that's not really, it's a very, very specific use case, so you shouldn't mind. Question, can we use the teacher forcing during evaluation after training? Raise your hand if you think it's yes. Raise your hand if you think it no. Okay. What kind of people are those who didn't raise their hand? It's a further more sinister answer. Okay, someone wants to tell me why? Why is bad? Yeah? No, this evaluation is not inference. But yeah, this is actually an interesting time. During inference, you just cannot do it because you're generating, so you don't know what's the output. But during evaluation on the test set, you want to test it. So if I just feed the answer, I'm basically cheating. I'm revealing the answers. So far, everything understandable? Any question? Then we can go with the quiz. So we can now go to attention. And this is a super, super, super cool concept. It's kind of the core of NLP even today. There's this like very famous paper called Attention is All You Need by Vasvani. I don't actually remember if he was the first one introducing attention for the task of machine translation. Anyway, everyone wants to be Vasvani because the paper is from 2017 and it's still state of the art. It just makes citation every second. Okay, so let's say we use our encoder-decoder with lots of fancy layer, whatever, and we do machine translation. What type of sentences would it perform bad on, and why? Anyone wants to guess? Where? Yes?
Yes, the longer the sentence, the poorer the state description will be.
Exactly. We saw it before, and it's the long sentences. So the usual problem of long dependencies. If I need to translate 300 words and word 297, there's some information from word 50 for word 15 for word 100, whatever. It's a problem because the hidden state of an RNN is still finite. It doesn't matter if it's two RNNs and we call it an encoder-decoder. The more tokens you read, the more these states become some kind of aggregation rather than, memorizing individual tokens. So at the end, what happens is that the decoder initializes with this final state, we saw it before, and that state must summarize the whole sentence, but it's quite hard. So to give an intuition, if you have 100 dimensions, you can probably represent 2 words with those. If I give you 1,000 words, that's another thing. So the more text you process, the more this gets harder. So the question is, what if there was a way to look at individual states rather than just the final one and give them some more or less importance? That's exactly what we want to do with attention. So the attention spans from the idea of how you, in fact, pay attention when doing basically anything in your life. There's this important quote by Christopher Pola to say, when I'm translating a sentence, I pay special attention to the word I'm presently translating. When I'm transcribing an audio recording, I listen carefully to the segment I'm actively writing down. And if you ask me to describe the room I'm sitting in, I'll glance around the objects I'm describing as I do so. So that's the intuition. The idea is that the decoder does not need to store the entire source sentence in a single fixed state, but it needs to understand the most important part and pay more attention to it. So this attention mechanism allows the decoder to look at all encoder states and decide how important each one is, and then weights this importance somehow. Without knowing yet what the attention does, let's build the intuition with an example. So we have this example when we want to translate a friendly dog into German. And again, we still don't know what happens in the attention, how this is done. But one may argue that to produce ein, you need 2 things basically. You need to pay attention a lot to A, which is the main article you're translating, but also dog, because if instead of dog there was something else, maybe that ein will change in another way, right? The same way that some verbs are influenced by whether this person is singular or plural, right? Similarly, you could say that friendly basically needs to yes, pay attention to friendly, but also to dog, because I mean, a friendly, two friendly, it depends on the language. But in this case, we need to understand there is dog at the end. Again, this is just very, very, very high level. And oh, sorry. Yeah, and that's basically it. So, but
Sorry.
yes,
Yeah, quick question about this slide. What are the alphas supposed to be?
the what?
Yeah, like
We don't know yet. We're gonna see it in a bit. Don't worry. The alpha is gonna be clear in a bit. I also forgot to put animation in the ears, but whatever. Okay, then it's fine. Yeah. So basically we have an encoder-decoder network, and what it produces: states for the encoder, states for the decoder. Pretty okay. So if you get a time step t at the TF token, what we want to obtain with attention is a fixed size update with respect to the whole sequence, representing relevant information from the past. So we have the decoder state at this time that we are considering the current, word, and whole the encoder states, because again, the encoder processes the whole sequence. So we have all of them. We want an update that we're gonna call A, like attention, at step T, which tell us roughly how relevant the set of states is with regard to the state of the decoder, the set of states of the encoder. So basically, how relevant each encoder state is to this specific state encoder. How do we do this? Yeah, and this will be AT. We're gonna see later how actually is obtained in the end. But as a first step, what do? We compute what is defined energy of the attention. And this is like how similar or relevant the two vectors are. In our case, of course, the vector are the state at step T of the decoder and one of the encoder states. Intuitively, you need to do this for every single state of the encoder. So we have basically this thing that we're going to call alpha et of IT, which is the energy that is somehow the similarity or relevance of the EF encoder state with the TF decoder state. So how do we calculate this energy? If I tell you that energy is like the similarity or relevance, anything from the previous lecture which is inspiring? Yeah? Cause similarity, or to better say, the dot product. So yeah, common choice is just you do the dot product of the two vectors, okay? So in theory, if you know two states are very similar, if they point in the same direction, their dot product should be very high, their cosine similarity should be very high. And the intuition is they want to know how important is the encoder state at step I to our current decoder state at step T. Then we do something else. We don't just keep the dot product as it is, but we scale it. So we scale the dot product to preserve the scale of variance. And what we do is, again, this was what we had before, and we divide by the square root of the dimensionality of the decoder state, as in how many dimensions there are in the state vector of the decoder. Why do we do that? Because the dot product gets very big as much as our values, as our vectors have more dimensionalities. Doesn't matter if the values are small, you're still gonna sum them, right? So if you have a vector with 1,000 dimensions, that's gonna grow a lot. Why is this a problem? And I'm saying this a lot, but we're gonna see it in the next step. For now, no? Yes?
Why do you say square root of the dimensionality?
Because we're gonna see it. Why in the next step? I know, guys, I know, it's frustrating, but I need to, yes?
Can we normalize for the dot product?
Yes. Can we normalize for dot product? What, dividing by the module?
The two vectors, so the dot product ends up to be -1.
Yeah, we could normalize in other ways, but this is done in this way, so apparently it works. I can research into this if other normalization works as well, but I'm gonna give you a good reason why you need to normalize by this. In general, just know that it's a scale, and when we are scaling something, it's because we want to flatten a bit the values. But again, we're gonna see it in a bit. Also a note, the use of DDEC here is purely for notation because, as you know, the dot product can be also done between two vectors of the same dimension, right? The same dimensionality. which means that to implement this attention, you need the decoder and the encoder to have the same exact dimensionality. So the thing that we saw before, when you have Italian 100 dimension and Spanish 50 dimension, it doesn't work now. It needs to be meshed. So dot product, scale the dot product. First step, we're gonna turn this into a probability distribution via softmax. So what we're gonna do is gonna have this alpha t, which is the softmax of all the previous alpha hat that we obtain, right? So basically you obtain an alpha, which is a scale dot product for each encoder state, 1, 2, 3, up to n, assuming a sequence of n words, with that specific decoder state. These are called the attention scores. Now we can discuss why do we need to divide by the dimensionality of the decoder. Okay, so I gonna just be honest. I don't honestly expect you to motivate this in the exam, but I could not put the dog because you need to do this. You need to know this, but you probably don't need to know this. But I'm gonna still tell you. So softmax becomes very, very sharp when the value gets larger. So for example, compare the softmax of 1 to 3 with the softmax of 10 to 30. You can see that, sure, there is still a sharp difference here, 0.09, 0.24, 0.66. Most of the weight is on the biggest value, but look how it becomes here. This approximation, basically you have pretty much all the value there. So what happens when the softmax becomes sharp? The model becomes very overconfident because basically you put all the weight in a single token, or like 99.9% of the weight. And this hurts learning because typically it's not true that you should pay attention to only a specific token. This could result in you naively paying attention of the token you're translating. If I translate I just pay attention to I, or just hurts learning in general. Now, why the square root? Because it preserves the scale of variance. The variance of a dot product is kind of increases proportionally to the dimensionality of the evolved vector, which in our case is ddec or denc because they are the same thing. And what is the variance? The square root of, what is the standard deviation? The square root of the variance. So that's why you use the square root of the decoder dimensionality. So hopefully the mathematics in the room are now happier. If they're not, please don't ask me more. I'm not a mathematic. I might embarrass myself. But no, jokes apart, any other question on this for fun? Okay. We have a fourth step. Fourth step, now we have the importance of each encoder element. So we have this alpha t that you remember is a vector and has these elements alpha I. I don't know how to call this without, it's so confusing. Alpha over t, we could call it alpha over t for all the I states. So how do we produce the final summary of what is important? Well, you may argue that now we have a weight of each encoder state. So why don't we do a weighted sum? And these are called the attention weights. So you're gonna have the final update A over T, attention over T, as the sum, weighted sum of the, how do you call it? The importance, sorry, of each encoder state to the actual state. So basically you're weighting each encoder state by importance based on the attention you think you should pay to it. And finally, we concatenate this with the decoder state. And this is the initial formulation of the dot product scaled attention, which is so far, even today, one of the most famous ones, most used ones. Any question? Yeah.
Is this still applied to the RLN?
Sorry?
Architecture? Is this attention still applied to the RLN architecture?
It's applied to the decoder of an encoder-decoder. Yes?
Yeah. A question about this formula, like the alpha TI. Is that
Alpha TI is the ith element of alpha T. So
so it's already softmax.
Yes, it's indeed a softmax, which acts as a weight.
Yep.
Okay. Anything else? Okay. This is a little example. So that basically at any state, given the current decoder state and the whole state of encoder, did I say that well? Given the current decoder state, sorry, and hold the set of encoder states. You compute the output of the attention mechanism as via this weighted sum, and then concatenate it and feed it to the next step. So what will happen is that you will have your nice encoder that produces a final state. Then you would look at all the encoder states, produce this weighted sum, and concatenate it to your state decoder. And then you produce an output. Now we can use the output to feed it autoregressively to the decoder. Again, do the same stuff. And the attention is going to be a bit different because, of course, we're producing a new word. So we're going to need to pay attention to different elements of the input sequence. And you concatenate and produce something else. Now, does it work? Does it make sense? It works really well. So this is an extract from one of the papers that first used attention for machine translation specifically. And you see the blue score, which is not for exam relevant, but just to remind you, is like an n-gram overlap metric for machine translation. Basically, it tells you how much your translated sentence kind of has the same n-grams of a ideal translation, your ground truth. And you can see that this is like the line of when you're gonna use attention compared to the others. And you see that basically the blue score is the higher the better. It stays pretty much stable, while the other architecture with attention just drops. Typically drop after 20 n-grams or 20 grams or something like that. So it actually works. It let us model much longer frequencies. There's also an argument on whether you can use attention as an explainability matrix. So there is this thing that lectures ago, we saw this very cool visualization of the logistic regression. You have the line that curves and then the sigmoid that's super understandable. But now we're dealing into many parameters. Nobody has a clear idea of what is happening inside, right? It's not easily understandable. So in theory, if you try to highlight the tokens we get the most attention, let's say for a sequence classification, you get some insight on what the model is reasoning. So for example, in this, they see there is a problem. The authors argue that there is a problem because you want to label this person based on their job. Their job is a physician, but the model seems to be attending mostly the misses rather than the actual job. And what they say is like, okay, we fix it. So we retrain the model by forcing the attention of the tokens that we know that are more valuable. And now, it cares more about medicine and other tokens. So some people argue that by attention is explanation. Some people argue that it's not. I don't have an answer. I'm going to leave it there as food for thoughts. Yes?
Yeah. Okay, well, I don't really understand what the difference is supposed to be between original and ours, in the sense that, like, what do they do to get it from paying attention to miss?
You force it. You force the attention. Basically, you retrain, you force the attention to pay a specific tokens instead of letting it develop.
So train the child to pay attention.
Yeah, it's a post fix basically. You have a trained model, and your model somehow picked up some spurious elements that say, oh, the best way for me to predict that this person is a doctor, a physician, is that you refer to her to miss, which of course doesn't make sense. That's also the argument. Maybe you can do this and then lower performance is always a tricky trade-off. But if your performance depends on spurious patterns, probably your performance is not good to start with. Yeah.
I'm not sure I understand very well. Do we use like the set attention during the training, or how do we?
So how does it work? Normally, how do you come to this?
Yes.
You train and you let the model try to measure, because basically it's gonna try, and it's gonna try basically during the training and back preparation, it's gonna learn which tokens let the network generate more accurately like this, okay? And for some reason, this network understood that if it focuses on this, it can predict physician more confidently, more often. So it boosts the accuracy. What they do is just to do a second pass of training, which they force the model to still predict physician, but to focus on those tokens instead, like medicine, for example.
How do they get? I mean, let me try to rephrase it a little. How do we get the correct attention?
Okay, how do we get the correct? But you mean how do we get the correct attention instead of how do we train it, or how do we know which tokens it should focus on?
Yeah, how we know zones it should focus.
Well, in this case, I assume they made some annotation.
Okay.
And they just realigned it. So basically they say, okay, this person is a physician. To be honest, Miss doesn't make sense because it's Mr. Nothing changes. I just put it on medicine, Memphis. There are some other words maybe about a specific institute. It's just manual annotation. Yes?
Yeah, but the architecture of the model,
Yeah.
go back to the first. Right, so
Yeah.
the state of the encoder gets, like, for example, the first state gets fed to the second state and so on.
It's just a normal RNN, yes?
So why couldn't we just sever these connections and let the model just predict a state on that one word? Hey, nice, dog.
That's interesting. That's interesting.
Yeah.
Okay, that's interesting. So your colleague asks, why do we need to connect these states? Why don't we cut these and just have every cell independently model a state, right? Well, the point is the power of an RNN is the states needs to be accumulated because every cell sees the whole past. We're just saying that the more you process, the more the state is going to become more an agglomerate rather than individual tokens. Maybe there is still some information about token 3 versus token 1, but overall it accumulates. So it's just good to let it accumulate and generalize to see the whole sequence. That's still needed. Otherwise, you will have, like, I don't know, something that just produces, it's a very limited computation, right? You see?
Yeah, for learning how context affects the state. But then I was thinking about you could argue the other way, bro. I mean, why wouldn't the word A depend on dog? So the state of dog should influence A, for example.
Yeah, okay, so basically you say we should model it in a more fine grained way, but that's super complex engineering at the engineering level. Because first of all, it involves that you will have a way to dynamically make this connection. You want kind of a dense network that learns how to connect nodes because maybe A and dog are more. It's a very interesting question, but I don't have an answer actually. Maybe we can discuss after the lecture, or I can do some research on it. Or if you do some research, let me know. I'm also curious. Yep.
Can we use the purple blocks into decoder model? Because right now decoder's generation doesn't utilize them.
I didn't get the question, sorry.
When first block of the decoder
Yeah.
is back 1. It's inputs.
Yeah. No. Right question, sorry. Basically, you're asking, what about this? What's the state, the initial state of the decoder? Because this is an input, this is not a state.
Yeah.
The initial state of the decoder is usually still definite state, but that's good because we learn how to weight them. So it's a starting point. So the more.
My question is, can we concatenate the purple blocks to the decoder space instead of concatenating?
It is done. This is actually. This is concatenating the purple, which is the attention, to the decoder state.
Yeah,
it's literally what we do.
As back to, does that process A1 or A2? I guess after the lecture.
Sorry, maybe maybe this shouldn't be called really A1, A2. Maybe it's from an old figure that recycled and it's a bit confusing. But no, it's actually. I'm a bit lost now, honestly. What's the problem?
Okay, I will write it. Yeah.
Or maybe come to me later to the lecture. Is this confusing for anyone else? But just to clarify, this is just the thing you obtain, and then you concatenate it with the state of the decoder normally produces. Okay, so just clarify. You just do that. Yes.
This case, the input and output state line. Again, how.
Oh, it's just an example that they are input and output at the same length. I didn't have enough space to do like.
Yeah, how.
You generate end of sequence and you stop. Because every time you're just refeeding its own output. There's no future tokens to read because the whole sequence has been entirely processed here. You see? Okay. Okay, so again, now we need to generalize a bit attention because we saw a very, very specific way of representing it. So there are three components, which is also how attention is usually normally known. The query, which is again this function of the state of the decoder, and basically it is the state representation based on which we are looking information. So basically, what am I looking for? In this case, like decoder step T, which I'm trying to understand what could it benefit from. Then we have the keys, and these are related to the encoder state, and these are the representation we compare the query to. So how relevant is this information to that specific state of the encoder? And finally, you have the values, which again is the encoder states. And these are the representation that we did the weighted sum over given the attention score. So what information do I actually take? So I have this thing, I'm looking for what's more relevant to this. I compare it with all of these, and then I understand how much of all of these I should take, right? These are arbitrary functions or neural networks, like a feed-forward layer or whatever. We're going to see in a bit why we might want to further add another step of processing. And basically, you obtain this. You have your update, which starts from here, the alpha at IT, which is, okay, sorry, which is again the query, which is the decoder, with the key, which is the one specific encoder state. And then you divide, you scale it. You apply the softmax, you obtain alpha at step T, and then you do a weighted sum, which is this is actually A. Oh no, I'll correct it later. 80. The difference with before is that before we didn't distinguish between keys and values. If you see, we have SEnc here, which is the keys, and then we have here, which is the value. So now we're calling these two different things. So this is the general formulation of attention, which you see everywhere in the papers, and you should know mainly. Some other stuff. You can make some implementation variation where you implement the attention mechanism. And these are mainly three. The first one is the energy. So we saw the dot product. Maybe we can calculate the relevance in another way. There's also parameterization. So if and how we apply transformation, those famous F. So what if instead of doing the dot product, I do the dot product and then I apply a transformation to it for some reason. And finally, the direction. So right now, you saw that basically each state of the decoder attends to all the states of the encoder. We could choose that we don't want to pay attention to all of them, but so only some of them. So I'm gonna present a couple of alternatives. This one, we saw it already, the dot product scale attention. If we remove this, it's not scaled anymore. Of course, it requires that the query and the keys have the same dimensionality. We saw this before. And the cool thing is that it gives us no additional parameters. So we get it for free. We don't need to train additional stuff. We don't need to make our network heavier, longer to train, blah, 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 blah. We have the banal attention, which is basically a hyperbolic tangent with two transformations, as you see here with the matrix. It's cool because now we don't have these requirements of having the same dimensionality between the input states, because we can just transform them with the matrix. But we also have some additional parameters with W1 and W2, and why it could be good, because you can model some further, more complex pattern by doing this transformation. And finally, we have the bilinear attention, which again, which again has no requirement of the dimensional states and have these additional parameters. So why you might prefer one or the other, it really depends. Today, as far as I know, the dot product scale attention is still the basic one. Is also, I think, the first one that has been introduced. Some others may work in some specific setups because your data looks different, because you need to model a specific relationship that needs a bit of linearity or another matrix of weights. Really, people just try and see what happens. But as far as I know, most of the people, when it comes to downloading a model from Hugging Face, they just keep the default one. So parameterization choice. I forgot the admissions also here, but whatever. Remember that we have these arbitrary functions, which can be neural networks. What are the most common ways to do this? Well, usually it's a linear transformation. You can also make it nonlinear. The intuition is that in theory, what if the states also contain something I don't care about, like that information that is not relevant for the similarity or confuses the similarity, or it makes it harder for me to retrieve correct information. Then I pass it to other formation, and maybe this can be flattened or mapped to null in a specific dimensional space. So it's just on filter processing. And finally, the direction choices. So now we have two main ways. This is called cross attention, where basically what you're looking comes from another sequence. So now, for example, here you see we are translating. Every time you translate, you're looking at the states from another sentence, which is the starting one, like English when you're translating into German, for example. The alternative is self-attention. In this case, everything comes to the same sequence. Now, sometimes we'll see it next in a couple of lectures. You may have a mask on this attention so that you can check only a certain part. But basically, cross attention, you look at another sequence, like you're in German, you're looking at the English one. Self attention, you're looking at the sequence itself. And what's next to this? Nothing, because this is the end of the lecture. So this was about attention. Rest well for the next week, because the Transformer and BERT lecture is heavy. There's gonna be a lot of stuff. And yeah, I'll see you next week.